Hi all, welcome to online spoken faculty development program and advanced communication laboratory. So this will be session 1, experiment number 2. So what we are going to see is, we are going to study and we are going to measure the numerical aperture and mode characteristics of the fiber. So before we just move into this numerical aperture sessions, we should know what is numerical aperture. Simply we can say it is an ability of the fiber to collect the light. We can say a collecting ability or the light gathering ability of the fiber will be nothing but the numerical aperture. So we should know why we have to study this characteristics. So the important reason why we have to measure this characteristics is, so it will have an impact in the V numbering or V mode of the fiber. Technically speaking, we will say that is a normalized characteristics or normalized frequency, so which is used to measure the mode of the fiber. So next important thing is this numerical aperture measurement is also needed to measure the acceptance angle of the fiber. That is the maximum angle which will be allowed by the fiber to move along the core will be nothing but the acceptance angle. So we have multiple reasons or multiple effect in order to measure this numerical aperture. It's a very interesting characteristics. So let us see the practical sessions, what we are going to see. So for measurement or for calculations, I just told you it is a light gathering ability of the fiber. So what we need is, we need a light. A light will be in the form of LED or laser and gathering ability of the fiber. So next important thing is fiber. So one is light, other one is fiber. So these two important things is essential for measurement of numerical aperture calculations, right? So I'm just going to introduce you to a simple setup for measuring this numerical aperture. So theoretically, maybe if you just come across that we have multiple methods to measure the numerical aperture. A commonly used method will be nothing but the scanning detector with the rotating stand. That will be the first method, and the second very easiest method will be the trigonometric method to determine the numerical aperture. So for our laboratory, it is more easy and it is more convenient to use the second method, that is trigonometric method to measure the numerical aperture characteristics. What are the basic requirements to determine this numerical aperture through this trigonometric method is, as I just told you, one will be the light, other one will be the fiber, that is light gathering ability of the fiber. So we need a light in the form of LED or laser, and we need a fiber, and especially for this trigonometric method we just need a stand, that is numerical aperture measurement stand. So these are all the three basic requirements to determine the numerical aperture. So let us move to the practical sessions. We can measure this numerical aperture. Yes, the first important thing is we are just going to give an input to the transmitter, that is fiber optic transmitter. So the basic requirement, as I just told, we need an light in the form of laser or LED. For our lab experiment, LED is more than enough. So next one will be the fiber, so through which the light is going to transmit, and the third one is this stand, numerical aperture stand, which will have the scale on it, right? So very simple. I'm just going to on the switch, and I'm going to take the light from the laser, so that is from the LED. So the light is moving towards the stand. So we have an option to unscrew and screw through this numerical aperture stand. I hope you can able to see this, right? So I just fit the fiber through this screw arrangements. So now the thing is, we are going to measure two important things. So one will be the D, value D, which is nothing but the distance between the tip of the fiber and the stand base, right? So this is nothing but the D. So next important thing is the value of spot radius. I hope you can able to see the spot radius, right? So this one will be the spot diameter. So D by 2 will be nothing but the radius. By means of multiple iteration, by means of changing multiple values of D, we have to find the value of R from the spot diameter. So D and R is more than enough to measure the value of numerical aperture. So the very simple formula is R divided by R, that is spot radius, divided by root of R square plus D square is nothing but the numerical aperture. So what we have to do is, by changing the positions, by changing the distance, we have to measure multiple values of this numerical aperture, and from these multiple values of numerical aperture we can able to find out the average value of numerical aperture. So this numerical aperture will vary based on the fiber characteristics. We can say based on the core and the cladding of the fiber. So based on this fiber, what we are going to use, the numerical aperture value will vary. From the value of numerical aperture, we can able to find out the acceptance angle. So this is all about this experiment. Let us move to the calculation part. Now let us move into the calculation part for the measurement of numerical aperture. So the various parameter has been listed out. So D is the first important parameter. So D is nothing but the distance between the tip of the fiber and the numerical aperture stand base. So D has to be measured. For each value of D, we have to find out the value of AB and CD, that is horizontal spot diameter and vertical spot diameter. So from the value of AB and CD, we have to measure the radius. So radius will be equal to horizontal spot diameter plus vertical spot diameter divided by 4. So we have to measure the value of R for the value of D. At last, the numerical aperture can be measured by means of a simple formula. Numerical aperture is equal to R divided by root of R square plus D square. So I have just noted down some sample readings. So let me consider the cases. The value of D as 1. For the value of D1, I am going to get the value of AB and CD as 1.8 and 1.8. Obviously we know that the radius will be equal to 0.9. So for the value of D as 1, we get the value of R as 0.9. So simply substituting the value of this D and R by a simple formula of numerical aperture is equal to R divided by root of R square plus D square. So the value of radius what we have obtained is 0.9 divided by root of 0.9 the whole square plus the value of D will be 1. So 1 square. So which will be equal to 0.668. So similar with respect to this conditions, we have to have a multiple iteration. So let me say an example as 1.5, 2 and 2.5. So for various values of D, we have to measure the values of AB and CD, and from this value we have to measure the value of radius, and by means of D and R we have to note down the numerical aperture. So for our case, let me consider the average value of numerical aperture is 0.64. So the interesting fact is, from the value of numerical aperture we can able to calculate the value of acceptance angle. So the simple formula, theta A or theta max will be equal to sine inverse of numerical aperture. Let the numerical aperture what we have found out will be equal to 0.64. So hence I am just going to substitute this value. By means of substituting this numerical aperture, I can able to find out the value of acceptance angle, which is equal to 40.28, which is merely equal to 40.28. So this is how about the calculation part. So for multiple values of distance, we are going to measure multiple values of radius. From the iterated value of d and r, we are going to determine the value of numerical aperture. The average value has to be found. From the average value of numerical aperture, we can also find the value of acceptance angle. So this is all about the tabulation part. So a very simple trigonometric method, so by which we can able to find out then very important parameter, one is the numerical aperture as well as the acceptance angle. So this is all about this experiment. So hopefully we can see the next video. Thank you.